Howdy and welcome back. So a brief overview of the STL, and you'll see why I'm kind of choosing to do this at this point momentarily. But here's some, I don't know, fun facts about the standard template library. There were 16 containers implemented within it since the C++11 standard. So I guess read since as at the time of the C++11 standard, there were 16 available containers. There were 5 iterator types, and there were 80 plus algorithms that you could apply to those containers. And some of the algorithms, I'll go ahead and just point out, they were dependent on a container implementing a specific type of the iterator. For instance, again, if you think back when we talked about, okay, a singly linked list iterator, it might only be able to go forward because that's kind of what you had based on the underlying structure. Whereas a doubly linked list iterator could go back and forth. You could have that decrement operator defined as well. Finally, the vector, it could go back and forth because the underlying representation, how we're storing our collection of elements within a vector is just an array. So not only could you go forward, backwards, pretty much at will, as long as you stayed within the bounds, you could also have random access and jump directly to a specific point in that representation, something you could not do in a singly or doubly linked list, because again, those nodes are scattered all throughout memory. And to access, say, the fourth node, you have to follow the first, second, third to get to the fourth pointers. So this is the STL model. This is where we were going. This is what we were building up. The underlying implementation of the STL model was that we want to implement algorithms that are able to manipulate data, but don't have to know a thing about the containers they're operating on. So maybe you've used the standard, let's say you had some vector int v1, 2, 3. If you wrote something like std find, assuming you pounded and included algorithm and did v.begin, v.end, and let's say you were searching for 4. Let me draw this out quick. v.begin returned an iterator to the first element within this collection, and n returned an iterator to one past the last. We'll go ahead and revisit our find definition here shortly, but understand that we were essentially iterating through this our vector and comparing each of the elements against the value that we were looking for. And how would we do that? Simply by dereferencing the iterator, incrementing it if it did not match 4, and continuing this process until we arrived at the end. So what we're going to see is each standard library container is going to provide you with its with a couple of sets of iterators, one to the first element within the sequence through the begin function member, and end is going to provide an iterator to one past the last element within that container. So containers, because they're going to provide iterators, are going to be able to be applied to these algorithms, despite the fact that containers know nothing about the underlying algorithms. So how they're going to interact, algorithms and containers, will do so when we're using the standard template library through iterators. So I believe this is getting towards the last slide here. How do we ask a container for its iterator? Well, recall a pair of iterators defines a sequence, and they're going to allow us to iterate through different types of containers the same way. You can ask any STL container, whether it's a vector, list, or otherwise, for its iterators all in the same way. If you want a read-write iterator such that you could update, say, a data value at a particular position, you would use whatever the identifier is .begin to have an iterator return to you to the first element within that sequence, and to return 1 to 1 past the last. Let's say that you needed to, work with, maybe you've passed some sort of collection by constant reference. So you can only work with, say, a particular object in a read-only capacity, or you're choosing to do so because you do not need to write to it. Well, you can interact with constant iterators, which will allow you to access the data. They will allow you to move forward, just like the read-write iterators. However, they will be read only in the sense that you won't be able to update the data at a particular location within the specified container. Now, finally, here's kind of just brief run through of how you can use these. So if I have a standard template library vector of integer values v, initialized with the integer values 1, 2, 3, 4, we could do something like a for statement. We could do auto iters equal to v dot begin, while iters not equal to v's end, hit the body. This is just going to output the value stored there. So dereferencing the iterator is going to give you the value. So we'd have print 1, we'd hit this part of the for statement's head, increment the iterator to move to the next element, check for at the end. If not, go in, dereference, print the value, and continue this process. Now let's go ahead and see, I mean, I kind of alluded to this, but let's go ahead and apply this to an STL algorithm. Find is going to return an iterator to the element if it is found within the container. Otherwise, it will return an iterator to one past the last element. So I'm going to go ahead and use auto here. It just makes this easier. I'll let the compiler figure out what the type of the iterator is, and we'll hopefully show why this is a little bit later in the course. But iter to result is equal to, it's initialized with the result of the standard template library's find algorithm. We pass in the first an iterator to the first element in the sequence. We pass in an iterator to the last element within the one past the last element, which we're considering during this find process. In this case, we're searching through the entire vector and we're looking for 2. So dereferencing the result here, and I probably should have checked to ensure that, hey, iter to result is not equal to v.end before I attempted to dereference it, because again, remember, end is one past the last, which could prove problematic if iter to result is the end. So in this case, 2 was in that collection. So dereferencing 2, because again, this function will return an iterator, will give us the data to which it points, which is 2, and we observe that result. So that's the end of, I guess, today's lesson. Hopefully you found it informative. Hopefully iterators make a little bit of sense. Maybe kind of now you're seeing some of the utility of using them to connect containers with algorithms. And if for those of you who were using things from the algorithms library early in the course, hopefully at this point you understand a little bit more as to what was happening when you were invoking them. So see you all tomorrow.